we have this thing called singular learning theory, which says some stuff about how Bayesian learning on neural networks works, which is not how neural networks actually learn things in real life, but it's any learning algorithm whatsoever. Maybe that's a start. But singular learning theory makes some sort of assumptions in the way it's set up, where like one very big assumption is all the data that your learner, your inductor sees is assumed to be sort of drawn independently and identically from the same distribution. So like IID sampling. And that is not how neural networks learn in real life. And that means that you can't use some of the sort of central theorems of singular learning theory to maybe answer the questions we would actually like to answer. So, for example, say we've, with Bayesian learning, somehow trained a neural network to classify us a bunch of pictures of animals. And all the pictures were taken outdoors. And now we ask, how well will this neural network do when we now show it a picture of an animal taken indoors? Will it still classify it correctly or not? And you might hope that singular learning theory has an answer to this, but sort of on paper, I think it really doesn't. So it has a theorem for telling you the prediction error of your network in distribution, if I draw another animal picture taken outside, but not out of distribution. Like all of what singular learning theory says is sort of formally about the infinite data limit in distribution. So it would maybe be neat if we had some way to talk about Bayesian learning on neural networks that didn't require this AID assumption. And well, another field of math that talks about learning is algorithmic information theory. And algorithmic information theory does not need this IID as assumption. So sort of the central, most famous object in algorithmic information theory maybe is Solomonoff induction, which is sort of this uncomputable thing you can write down on paper on how you make good predictions by just running basically all the possible programs that exist, these being your hypotheses, and then with Bayesian learning aggregating their predictions. And this framework is like uncomputable, but it doesn't need this IID assumption. Like this is not a thing in there. The central prediction error theorems about Solomonoff induction don't need that. So maybe it would be sort of useful if we could talk about Bayesian learning in neural networks in sort of algorithmic information theory style. And what I'm going to try to sort of show off here is how you do that and recover a theorem for the prediction error of Bayesian learning on neural networks that does not require the IID assumption, and it does not require the infinite data limit. And the way that we're going to be doing this is, after some initial setup of notation, I'll spend quite a bit of time talking about actually Solomonoff induction on programs, showing off how you can actually import it in sort of this typical learning theoretic setting where you have data and labels the data belong to that you have shown. And okay, does this work? Oh, I will try to maintain this mic-mouth distance. We shall see. And then I'll be showing how we can also bound Solomonoff induction, make it like actually computable, something we could actually really run if we had a very large but finite amount of compute to spare, and show off that sort of this compute-bounded Solomonoff induction still satisfies like sort of the core theorems that normal Solomonoff induction has, somewhat weakened form. And then, sort of at the end, we're going to turn around and sort of use what we've learned to work for like a very similar derivation as the one we did for the compute-bounded Solomonoff induction on neural networks, and we'll get out an error bound that looks very similar qualitatively. Okay, So just basic notation. So we are in a setting of wanting to predict labels from input data. The input data in our case is like some long string of zeros and ones, not specifying how many. And the labels are just always either 0 or 1. And sort of a task is that sort of these labels are generated from the inputs x according to some probabilistic program, we assume. Like, some program we could write down mu that computes you the labels from the inputs. Maybe also probabilistically it could have some random noise generator, whatever it's accessing. And then our task is we want to make some inductor that tries to predict y from x based on the previous y-x pairs it has already seen. And the first inductor we're going to consider for this is still going to be an uncomputable inductor, which is Solomonoff induction just sort of imported to the setting. So going to take ourselves a plain monotone unitary universal Turing machine, binary input outputs, two-way work tape. And now we're going to consider the ensemble of all programs with length exactly capital T bits, where capital T is some finite number. And yeah, induction is basically going to be, we're going to run all of these programs and see what strings they output and interpret those strings as sort of a probability that the next bit is a 1 or a 0. And the way sort of formally we do this is that we put like a little p read program before the actual program's p, and then put in the input data x. And all this p read program does is get the xn sort of onto the work tape and then reset the whole machinery. So that sort of standard Solomonoff induction can happen. And yeah, like I said, the program predictions are then the number it puts out is interpreted as the probability that yn will be a 1. And our prediction rule is, our probability for yn is given by summing over all programs, like all their predictions, weighted by how much we currently sort of trust that program, which is given by the data we have seen so far. And the way we get this probability here is we start from just, yes?
He runs p on xn and then what?
So p-read is basically, like, you want to give your programs at every data point the input xn to predict y with, but you also don't want to sort of, there's a sense in which the program p stays the same program between data points. So we sort of just append this prefix, which all it does is p-read puts xn onto the work tape and resets the internal state of the machine so that then the next thing that gets read is the first bit of p. It's basically just formalia for making the standard Solomonoff stuff go through in this learning theoretic setting. And yeah, so the way we compute how much we trust our programs is we just start with uniform prior over all the programs we have, which, since it's all the programs of length capital T, that means everything has starting prior 2 to the minus t. And then we're just going to use Bayes' rule to update probabilities based on how well the programs have done on predicting the data we've seen so far. And then we can get an upper bound sort of on how badly this prediction process can possibly do. And this upper bound looks as follows. Provided that the program mu that generated the labels y from the data x in the first place is a program that is describable in less than capital T bits, or total prediction error measured in bits of cross entropy across the first capital N data points, well, capital N can be anything, is bounded to stay below the k complexity of mu, so it's minimal description length, on the universal Turing machine we have chosen, plus the entropy of the process mu. We said it's a probabilistic program, so it's allowed to have just some randomness in the output that you can't predict. And that's the bound. And just as a brief sketch how you get this kind of bound, you start with the expression for the cross entropy between the inductor and the data generating process. You do a few reformings of the equations. You apply the fact that this thing uses Bayes to make its updates and an expression like that. And so the core fact that we're really using here is that since mu, we said, has some minimal description length smaller than capital T, there have to be at least 2 to the power of T minus minimum description length of mu different programs that all give the same outputs mu does. So the degeneracy, really, of mu is like the core thing here that makes this happen. And because of that, we're actually sort of assigning at least in our uniform prior over programs, prior 2 to the power of minus k complexity of mu prior to this data generating process already. And that means, if you plug that in, that as the inductor sort of makes mistakes, it kind of makes at most as many bits of mistake as it takes to sort of specify mu in our program space before it's sort of found it. And from now on, it can't possibly be doing worse than giving the outputs that mu would give. Okay, so that's our first inductor. And that was still an uncomputable inductor. Unlike standard Solomonoff induction, we said we take the ensemble of all programs of some finite length capital T. We didn't take capital T to infinity. But it's still uncomputable because some of the programs in the ensemble might take infinite time to run. So now we're going to make it computable in sort of the dumbest way possible, really. We're just going to put a time cap on how long our programs are allowed to compute. Let's call it small t. If they're not finished by then, we just halt the machine and discard the prediction of that program isn't counted. Same, we put a space cap on, it only gets to use some number of S cells. Formally, we put it in an S plus first cell. If you go there, program halts. And technically, to make it computable, another thing we have to sort of formally change compared to the standard setup of Solomonoff induction over probabilistic programs is usually you allow these programs to keep on sort of printing numbers indefinitely to specify the probability assigned to something to higher and higher float precision. Here we just cut it off to it gets B bits of precision then over. Yes? There is a space cap that is implied by the time cap. I guess I'm saying maybe you want an even tighter cap than that. All right, so we make all of these sort of restrictions on what programs we even allowed to run in a sense that we built into a new universal Turing machine M2, which is now kind of bounded universal Turing machine. And then we just do the same thing again. So we just take the uniform prior over all programs of length capital T, and we crunch through a little Bayes updates. And then I claim we get another kind of upper bound on the prediction error. And this upper bound looks like this. So for any program mu star included in a set of programs that our induction takes into account, so programs that are describable in less than capital T bits and don't take more than the compute resources we gave the thing to run, or cross entropy sort of prediction error across capital N data points cannot be smaller than the description length of this mu star plus whatever error mu star would make. So in a sense, up to a constant offset equal to the description length of the program, our inductor is at least as good as any of the programs it runs over. And this upper bound holds for any program mu star, but what's of course interesting usually is sort of the tightest upper bound, which is is there a mu star in the ensemble of programs we consider that can predict the data efficiently? Not perfectly, perhaps. It doesn't have to be the case that mu star equals the outputs of mu, but maybe there's some approximate way to compute the data and do not perfectly, but do well. And then this theorem kind of says, well, your Bayesian learner is going to do roughly that well as well. Yes?
There's two things that happened since the last formula, which is you introduced the bounded limitation, and now you're talking about any program including any step versus the program that assuming any step. Those things are just, you could have done this in a different order and this would have been.
Yeah, so you can also write this theorem down for the inductor on the previous slide. Just for the one on the previous slide, it's kind of uninteresting to consider any mu star except mu itself, because you have mu, we don't have mu. All right, so under what circumstances is your data efficiently predictable like this, that there exists a mu star that is sort of runnable in attainable amount of compute? I don't know. Empirically, it kind of seems like the world is not just sort of predictable in principle with simple programs, but tractably predictable. We can say more than nothing with the finite amount of compute we have. Why that is so, I don't know. But, oh yeah, this is just a side note. This cross entropy between mu and mu star, of course, you can decompose into the entropy of mu itself, plus then the KL divergence between the two. And one more note, so sort of the same way that this bounded induction still satisfies a weaker form of the prediction error bound Solomonoff induction satisfies, it also still satisfies a kind of weaker form of the UTM invariance that normal Solomonoff induction satisfies. So if we change out our UTM for some other UTM, that's also bounded, and provided that we have enough time and space overhead, our prediction error sort of only gets a little offset here from however many bits we need to specify the new universal Turing machine and the old universal Turing machine. And the overhead in space and time is just some constant for space and log t for time. So you might need somewhat more resources, but not exponentially more resources or anything. All right, neural networks. Let's do the whole thing again. But this time we don't take the ensemble of programs. We take the ensemble of parameter configurations that we can put onto some neural network architecture. So formally we say now our inputs are no longer binary strings. They're like some input vector to some neural network. The labels are still binary, 0 or 1. And we have some model family here, depending on parameters W, that maps the inputs to the outputs. Then further, we're going to assume that we have a prior on these parameters that just localizes them to some finite volume. So we have some hypercube here in parameter space. And our starting guess here is just uniform prior over all of those. I think you can probably also do it with Gaussians, and results don't change much, but it's just the simplest way to show it. And we make our Bayesian prediction now by running all the neural networks, taking the outputs, interpreters' probabilities, and weighting them by how much we trust that current neural network parameter configuration. All right, now my claim. We get a prediction error bound. And the bound looks like this. Our total cross-entropy error across capital N data points is bounded by the prediction error of any particular parameter configuration we run over, W star, plus, I'll get into what this exactly means in a minute, the description length of W star to tolerance epsilon plus capital N times epsilon. So what this means is you take the set of all parameter configurations where the neural network belonging to that parameter configuration gives final outputs which in log space diverge from the probabilities that W star gives by less than epsilon, where epsilon is freely choosable, for all possible input-output data pairs. So it's sort of, this W will never diverge from a chosen W star more than epsilon like any possible data. That's the definition of this set. And then this term here is just, you take the volume of that set, and you take the ratio between that and the total volume of a prior, and you take the logarithm of that. So it's sort of the number of bits to locate this little epsilon ball in parameter space, description length in parameter space, if you will. And the reason that I haven't taken the epsilon here to 0 just and left it open is because, unlike the algorithmic information theory case, where there's always going to be some measure on programs that do exactly the same thing as your chosen program U star, here it can be the case that the measure in our integral of parameter configurations that do exactly the same thing as W star could be 0. So we sort of have to allow for, okay, they have to be just within some tolerance. And our price for that is that we get this extra term, this n epsilon here. And this bound, of course, holds for any epsilon and for any W star. But as before, the thing that's going to be most interesting usually is, well, what's the tightest bound you can get? And that sort of means you want to go to some W star. That's a good predictor of the data. And you want to look at the bound for some epsilon that's kind of going to depend on, well, how much data you're looking at. If you haven't seen much data yet, then maybe you want large epsilon so that this term stays small. You don't have to describe your solution to very much precision. Whereas if you have a lot of data, if capital N is very large, then maybe you want to take epsilon very small, provided that this term grows sublinearly in epsilon, because then it's worth to make this thing small, even if this thing gets a bit bigger. Yes?
Could you just as well describe this in terms of the right side of this inequality, because the infimum of W's?
Yes, that would be sort of the strongest bound, I think. He asked whether I can just take the infimum of the right-hand side, and then that's the best upper bound. Or at least that's how I understood the question.
Yeah.
So sort of make maybe the connection to normal SLT more apparent. In normal SLT, we consider exclusively the case of Wn, big N here is very large. And that means we usually want to make epsilon small. We want to make it go towards 0. And then further in SLT, you have this neat theorem that your epsilon ball grows roughly, usually as epsilon to some power. And then you maybe want to choose epsilon equals 1 over capital N. And if you take that to infinity, this disappears, and this becomes some term of some prefactor, which kind of becomes the learning coefficient times log N. And in our case, maybe sometimes we still want to do that if capital N is large, but we can also not do that. We can also look at larger epsilons if we want at some finite data. And sort of compare the epsilon balls here a bit. Yes? Yeah. So compared to the sort of standard epsilon ball that defines you the learning coefficient singular learning theory, some differences here. We are looking at the set sort of all possible input-output data, not the training data set, because we said at the start there is no training data distribution anymore that we're assuming here. So we just kind of need to look at everything. Then it's the difference between these neural networks and some set reference neural network, not the difference to the data labels. And thirdly, it's a worst case epsilon ball. In SLT, usually you look at the epsilon ball of stuff that on average is within epsilon of your reference. Here we look at everything that is nowhere, no data point further than away than epsilon from our reference. Under all of those assumptions, do you still get the theorem that this thingy grows as epsilon to some power, roughly, as epsilon gets small? I don't know yet. I suspect under some conditions, maybe yes, but future work. If someone wants to jump on that, yes?
Yeah, so just bring it back, what you're saying is running this stuff to work, right, you're really relying on this C of W star epsilon F not growing quickly as epsilon gets small. Right? It has to be sublinear as epsilon increases. I guess one question I have is, like, kind of going back to like classical learning theory in the 90s, right? I mean, this looks a lot like an epsilon net, and the epsilon net's going to grow very, very quickly, right? Like, it's not going to have this property, if I understand correctly. But there must be some difference here which gives you confidence that it's not. Like, how does this relate to or differ from like kind of a classic like Lockman style epsilon net?
Well, one intuition you could maybe have is imagine you have like some really deep MLP or something, and actually you could solve the task with a like much shallower, much less wide MLP than you can imagine.
Shallower and wider, or shallower and less wide?
Shallower and less wide, sorry. Then you can sort of imagine embedding that much smaller net in this much larger net that you've got, and sort of all the little weights that you aren't using in your small net. You have like a lot of ways to set these to different parameter configurations without changing the final output. They're kind of open degrees of freedom, which means in that case, this ball is very large, which sort of tells you, okay, this C is small when, I don't know how to call it, I hypothesize something like the circuit complexity of your solution in the case of the deep MLP is small. Yes?
So if the net is very large, then what's the thing above the division line?
Yes, this gets large. So.
Large, but this one also becomes large. So shouldn't that count loud?
Yes, that's the point. Like the point is, unlike sort of some classical setups you could have in a neural network, you don't need to sort of nail down the more description bits, generally speaking, if you make your network like much larger. Like it in most cases will tend to stay a property of the complexity of the solution, not the complexity of the architecture you're searching on.
So you want, if you have an oversized network, you won't necessarily get the same.
Yes. Yes, that's sort of the nice property we get that, I don't know, if you're fitting a polynomial instead, you might not get. Yes.
Yeah, just to clarify, I mean, I think Britt asked about with linearity, but I mean, what we actually have, we have this log of this ratio.
Yeah.
So it's like the ratio, if you think of an epsilon net, it's going to be like some polynomial, like it's like the dimension.
Mm-hmm.
So the log is like, yeah, I mean, the exponent is the dimension. The log is that exponent. So what we're doing, we're comparing this exponent on the epsilon
Yes.
to n. In the previous slide, you had to add epsilon. So it's like, yeah, I mean, this is why people say effective dimension.
So I think I'm almost out of time, and
Okay.
I briefly want to get through the rest of this. Yeah, so I've said most of this stuff already, so we can skip that. Here's briefly the proof sketch for this bound. It goes through the same steps basically that we did for the efficient, the compute bounded Solomonoff inductor. When now at this step we are inserting the fact that there's this epsilon ball of points that give within epsilon the same results. So worst case, if we assume the epsilon divergence is always in the most inopportune direction for us, we still get at least this. Oh, I do? Well, that's awesome. I didn't know that. Then I have a lot of time for questions. Yeah, so just brief summary of the results we got. So the first result was Solomonoff induction brought into the learning theoretic setting. We still have this upper bound total prediction error that is like equal to just the entropy of the data generating process plus the description length of the shortest program that specifies the data generating process. then when we sort of did compute bounded Solomonoff induction instead, we kind of got out that we're now still bounded to have our error stay below the error that sort of the most efficient prediction program mu star in our ensemble would make, plus the description length of that mu star. And we also still got this sort of UTM invariance that you usually get a normal Solomonoff modulo needing, in the new machine potentially more space and more time. So it does matter somewhat more than it does a normal Solomonoff induction if you change UTM, apparently. And then we did the same thing with Bayesian learning on neural networks and got this formula. So, open questions that we maybe still have here. So one I already mentioned is the growth of this epsilon ball. Is there some conditions we can put on the form of the architecture and maybe what the input and output spaces look like, such that we cover that roughly as epsilon goes to 0, this grows proportional to some epsilon ball like this, where epsilon to some power lambda, which that's what you get roughly in singular learning theory. And then I guess this lambda prime up here would be, I don't know what to call it, distribution independent local learning coefficient or something like that. So my personal guess currently, based on talking to Edmund Lau about this on Saturday, is that probably at least for some cases we can get this, but it's probably going to require extra assumptions on the model family. We've assumed very little here so far about the model family. I don't think I've used even differentiability or anything like that anywhere. We might need that. And then another category of questions. So, these prediction error bounds for the Bayesian learning on neural networks and for a bounded inductor using programs, they kind of looked pretty similar on paper here, at least to me. How similar are these induction processes to each other? In particular, the strongest thing you may think you might get is, what if Bayesian learning on neural networks versus Bayesian learning on some universal Turing machine is as small as a difference as changing from one universal Turing machine to the other? You could, the reason that we are fine in algorithmic information theory talking about universal Turing machines, even though, my computer is not made of some two-way work tape or whatever. It's it's totally different architecture, but we are, it's one universal computing architecture, another universal computing architecture. Who cares? We have the Solomonoff theorem that tells us the overhead is just description bit length of the architecture and the other architecture. So it's all the same, really. Well, do we get that if we change between Bayesian learning on neural networks to Bayesian learning on universal Turing machines and back? So I don't know the answer to that question. My guess as to the answer is, in one direction, probably something like this is true. In the other direction, I think generally this is not true, but caveats. So in one direction, I think that this will be true because a UTM can just simulate any neural network architecture we want to make up. And yes?
Take out the uncertainty, so it's on the right-hand side of the then we start with a solution in UTM case the right-hand side doesn't include the reason why it's a strong bound of very synchronous. The right-hand side in the continuous case has an independent. What's your thoughts on this?
Well, I actually think this is not a very large difference, actually, in the end in real life, because another term that in real life you almost always have on the other side is, the error of your efficient predictor, which also grows usually linearly in capital N. Usually you're not in a setting where you can theoretically predict the data perfectly if only you knew exactly what parameter to look at. And then whether, you grow with N by, I don't know, you make like 1/2 or, I don't know, 1/8 bit of error per data point you see on average, or 1/8 plus some epsilon that's like 0.0001, that's really not that large of a difference anymore conceptually, I think. And so I think showing that, for example, if a neural network parameter configuration exists that would predict the data well, then the UTM, if we're doing induction in UTM, it can just go simulate some neural network architecture to some precision, and then we get out like this error bound from that it's going to do at least as well as this neural network predictor would, modulo more or less this set off for describing the neural network architecture and describing like the rough place in the neural network architecture prior where this predictor W star is. So I think this is like a non-vacuous bound, sort of. Now the other direction, I think generally we do not get, because we have, like I have so far not restricted what this model family F is much at all. Like we could be talking about polynomials right now. Is the uniform prior over all polynomials up to some degree equivalent to uniform prior over programs in the universal Turing machine? I don't think so. My suspicion is that you maybe do get some theorem like this, but not for all neural networks, but for very specific neural network architectures. My guess specifically is you get it for those neural network architectures that are expressive enough to simulate a bounded universal Turing machine. So for example, some deep RLN could maybe do this. Or if you take a transformer and you sort of run it IL style and chain of thought mode, it could do this. And maybe for those, you can get a theorem like this. I haven't gotten a theorem like that yet. I have tried for the case of transformer in IL style chain of thought mode. Didn't quite work out. Like there were annoying prefactors bigger than 1, basically, on this number here. Maybe if you think about this more cleverer than me, you can make those go away. That would be awesome. If you can't make this go away, I think that tells us something too. It would tell us that the condition to make your neural network architecture sort of as good as a universal Turing machine or equivalent to a universal Turing machine is maybe actually like more strict than just it can simulate a universal Turing machine. Maybe you need something in addition to that. Would maybe be interesting to know what that thing is. And yeah, I think that was all I had to say, and I guess past me figured I'd leave the rest of this for questions. I should also add, I am not at all confident that everything on these slides is original. I didn't find any of this stuff like one-to-one in the literature when I had to look around, but at least getting Solomonoff into learning theoretic setting and bounded Solomonoff stuff, I don't know, it seems like basic enough that I suspect this is like already somewhere findable. Yes?
I don't understand the bounding of precision. Why do you have to do this? If you're already bound, so normally there's a couple different ways we can formalize it, right? So either we have the probability from below, or we use probabilistic, right? But here, in either case, the precision is going to be bounded by the runtime of the machine, right?
Yeah, I guess that's true.
You have to write down the output rational number if you're using the lower dimension computation. If you're doing the probabilistic thing, then you're going to have to be precision to the negative t, because you don't get to use.
Yeah, like at the very least, it seems true what you said, that since I have sort of set the runtime to be finite, I have already automatically set the precision to be finite. Yeah, good point. I don't know, I guess now you have like an extra parameter to make that more stringent, if then the time cutoff if you want. But yeah, probably should just throw that out. Good point. Thank you. Yeah.
So can we talk bit about like to what extent we really do and don't kind of buy this basic setting that, you know, just saying mumble Solomonoff induction is equivalent to handling out of distribution kind of situation, right? Like in some sense, what you're going to get if you get, like let's imagine a setting where like the data initially comes from one distribution and then switches to another distribution after a while. So what's going to happen, right? Solomonoff induction is going to put a lot of weight on, you know, this early thing, and then some weight on this early thing for a long time, then something else. And like eventually you'll shift over and like it'll learn to adapt. And sure, it adapts optimally, but like something super like surprising and great about that. But also when you switch to this limited precision setting, you might be very often like ruling out exactly those machines that are even allowed to make those switches, because those are, you know, much higher complexity things that are unable to kind of figure out.
Yes. The point of this talk is not to say, look, all learning machines do good out of distribution generalization. Like the point is, here is a formula for saying something about the out of distribution generalization error of some machines. And I indeed expect that there's going to be many settings you can make up where this error sucks. You know, just make some data generating process, for example, that you can't well approximate with finite compute, or
to add on a little bit more, like your bounds were in terms of a single system that generates the data. So there's no out of distribution in your bounds per se.
Well, I guess the way sort of the Solomonoff worldview, if you want to call it that, thinks about out of distribution is that it sort of goes, well, some sort of fixed process made the data that, as you said, leaves like a lot of room for first the data does this thing and then later does another thing. Things like that often penalized in Solomonoff induction description length-wise? Yeah, probably less, at least by a few bits. Yeah.
I think in the clarification, because I was confused about this and it was explained a few days ago. So the mapping from X to Y is constant. That one doesn't shift, but which X you're sampling from. You can start by just sampling from X that is metaphorically in this room, and then you can suddenly switch to sampling from X that comes from across the street, like maybe temperature measures or something, and the map is still correct. And it's not gonna give you a tight bound in cases where you're generalized well. Does it happen?
I thought in our setting we actually didn't have a probability between X at all. Those were just given. And the data is actually a model of Y and given X. And that actually is not for later in the set.
So,
on the slide for me.
So what the theorem sort of talks about is it talks about there's some map from X to Y. It doesn't talk about how the X were generated. That's sort of left open.
But you say out of distribution. You don't mean that the map from X to Y changes.
Yes, that's not what I mean.
You only mean that the sampling distribution of X changes, right?
Yes. Any more questions? Yes.
Started the conversation. Well, actually, I didn't quite see exactly how that. Like I would expect it to change. Like I see how the point is not like
So I guess perhaps the price you pay here, if you will, for throwing out the ID assumption is that, all these bounds are framed in terms of you do as well as the prediction error of this thing that is in the ensemble of parameter configurations you run over, plus some offset terms. And the theorems do not at all tell you, well, is there a configuration in the set of things we run over that does well? Like, this is like not a question these theorems answer you. It just goes, well, here is how well the inductor does sort of bounded by how well any of the things the inductor runs over do. So I think this can sort of still be mentally helpful because, at least to me, in many settings where we do neural network training, it does seem like somewhat intuitive that, yes, for this task, there will be some parameter configuration for a transformer someone can make up that solves this task well. Maybe for another task, I'm like already intuitively, no, it's just too small. There's just plain no parameter configuration you could make that will predict this well. So it's not like you have like no sort of intuitive footholds to try to figure out how good your W star could possibly be. But yeah, it's not like you get a formula for it. Yes?
Like, instead of AIT, it is so we go through the other products, but the end product has to algorithm with the correlation that is maximally observed so it's like what you do is that there is a whole finding the worst case difference the X that is coded
Yes, Yes, I think that's a good intuition. It's a good way to put it, probably. I do expect that this bound has to always hold, right? That was the whole idea. So we have to sort of maximally pessimistic as we construct it. And indeed, let's say you know some extra things about what your out of distribution shift is going to look like. Like maybe you're not totally ignorant. Maybe you're like, okay, I'm going to throw in another image, but the image will nowhere have more brightness than this or whatever, because all the images or cameras take are like cut off to not touch this part of input space. And then in that case, you would get a somewhat tighter bound because instead of looking at sort of this worst case epsilon ball, you can consider instead the distribution of x and y's sort of conditional on none of the x's have brightness higher than this. So this is sort of the way I would say that you sort of soften this theorem to get like somewhat tighter bounds for specific generalization or degeneralization situations. Yes. So if in praxis you were to try to sit down and use SLT or whatever to try to sample these epsilon volumes, I would anticipate that I would often want to use extra information like this to recover not the worst case generalization error, but like generalization error conditional on some specific new situations. Yeah, very good point.
Again, the first term on the right-hand side should be that the number of bits that f would need to find the region of the parameter space that is like at least epsilon away from W star or all.
Yes, this is kind of how I would interpret it. Yeah. So maybe to sort of see, I don't know if this is helpful, but something I thought of in how to interpret this as a description length is, imagine you have Alice and Bob wants to send W star to Alice, and their way of doing this is just they have some shared source of randomness, and they just generate random parameter vectors, and eventually Bob's going to see, oh hey, this one's within the epsilon volume, and then Bob sets over the index of like what parameter vector Alice needs to look at, and then that's going to take as many bits as like log of the index that Bob needs to send, and the index is going to depend on the probability of random vector that you sample in this volume lands in this volume. Yeah.
So, let's talk more about the So I think for the answer to why Solomonoff resolves this out of distribution problem, I think it's just that the distribution of y conditional on x doesn't have to be independent time, right? You can have one program that works with the entire history, and maybe depending on the language, maybe x and y is a different distribution. map x t to y t. But in your formalism, I'm not clear on whether this is still true because it seems that you're talking about a program that maps x to y rather than a program that maps entire symmetry to y. So maybe this is a sort of value for me about the algorithm.
So consider this way, like the mapping from x to y doesn't change. Like this is the unchanging object, as in classical sort of induction. You can sample like different parts of the input space x to sort of explore different regions of what the mapping from x to y looks like. And it can indeed be the case that on the data you've sort of seen so far, you've only covered part of this distribution over x. Maybe the new data point is like somewhere entirely different in input space. And then maybe, you make a mistake because you got it wrong. But you can't get it that wrong because what the Solomonoff inductor is going to do, right, if you give like a sort of tight sample from like only a little subset of x, is it's going to make up the simplest mapping that fits that. And if that mapping is like already as simple as the mapping on the whole distribution, well, that's one. It's not going to make any mistakes anymore. If it's like a little bit shorter, then it is going to make mistakes when you show it like a new data point. But the minute you do, it's going to adjust to that and like zoom in by exactly one. If it's made one bit of error, it's going to zoom in by 1 bit on like the correct input-output map. And so I think, yeah, despite the inputs x here being sort of unspecified, so long as it is true, which is like a big assumption in this setting, that y is a function solely of the input x and some unspecified other random variable that's not allowed to have like mutual information, like shared distribution with the other x's, you still get the error bound.
I agree that probably still be talking about bound on the distribution performance, but normally all I've got to do is an online setting where you're not assuming that the y is happening inside.
IID? Yes, so I agree that there's some sort of extra information that Solomonoff in the setting I have specified is not using, which, it's not trying to look at what x's came before, what x's might come next. And I agree that, while you do get this bound, this does require that y is solely a function of x, that the x that you currently have, which in real life isn't always true. So, my point is not, this Solomonoff is still like always the best way to predict stuff. It's not. It's just, this is how we use neural networks in training. You give them an input vector, they have to give a label. And the point here is I'm taking Solomonoff induction to that setting and showing that, well, so long as this pretty strong assumption is satisfied, Solomonoff induction is still sort of has its standard efficiency properties in a sense. More questions? Zach?
Just to clarify that, I think this is really tricky and really on the number that something like I have something more simple than I want to like create one simple solutions. It sounds like it's in some way closer to like adversarial where some fixed x to y mapping and choose the x's in
Yes.
for us to perform badly and sort of non-IAD in the way that Solomonoff induction using ideas from those bounds, which is not like the version of Solomonoff induction. Bring it back to you're not really saying hello. It's not broken into it. It's not just a straight figure all previous explanation. Specifically predicting
Yes, like in my head, what I'm doing is I'm taking the standard textbook Solomonoff induction, and I'm sort of taking neural network training, and I'm going, well, let's change the Solomonoff induction a little bit, make it a little bit more like the neural network training, so that we can sort of see how it acts in that setting. And then perhaps that teaches us something about how we can think about the Bayesian learning on neural networks. Yes? Fixed distribution of x's. Well, yeah, if you're assuming now that the x's are drawn IID or something, then yes, then I expect to recover something that looks a lot more like conventional SLT. Yes, that's kind of the sort of thing that I thought Edmund was asking about. If you know specific things about the kind of data you might view next and want to know if you will generalize to that correctly, you can make your epsilon ball sort of a little bit of a more permissive epsilon ball. You can like say, oh, I really need to look at error on those kind of points. Yeah. It might be. Good question. I feel like a thing that might be helpful for answering that question is if people went and sampled some epsilon balls, like for actual, real solutions in neural networks, and compare the SLT sampling of the classic epsilon volume, based on the learning coefficient, versus this worst case one, how far apart are they? Yeah.
So, we have all these questions about X, and sort of what we want, as Solomonoff induction people, we want X to be the history, we want X to be the string. And so, your problem is just that you can't fit the string into the input to the neural net. But if the neural network transformer, we could fit it into the... So if we really want to make it more exact, why don't we assume that the neural net is a transformer and have that string?
Yeah, you could totally do that. The reason I sort of formalized it like this was to demonstrate to people who mostly think in ML, look, this is a way to treat the standard setting that you like thinking about. You can totally take this in a bunch of different directions, and as online learning may become more of a thing, you would want to do that probably.
We got to call it down, so thank you so much.
All right.